Josie. Hi, everybody. It's my great pleasure to introduce Professor Dongping Wang. I've known Dongping since I was a PhD student in Bangor in Wales. I remember him coming, giving me a talk, and I got excited. I said, can I get that model of yours? And by then, the internet was not that good, but he kept sending me these codes, which I had fun trying using them. But I would like to introduce Dongping as he got his first degree from National Tsinghua University in Taiwan, and then that was in 1970, and then in 75 he got his PhD from the University of Miami. His advisor was Chris Moore, one of the big names in physical oceanography. And then he went to Chicago.
No, Johns Hopkins.
Oh, Johns Hopkins. I skipped to that. And then from Johns Hopkins, went to Chicago. And in 1985, came to MSRC, as SoMAS was formerly known. And he was there until last year when he decided to abandon me. Because I've always worked with Dongping. We've always taught courses together in physical oceanography, and it was always fun. I must warn, for those people who are not familiar with Dongping, he always likes to pick controversial topics. So you're going to be prepared on this talk. And one other thing I must tell you about Dongping, which when he didn't tell me he was retiring, he told everybody. And I was surprised. So I went to his office and I said, Dongping, you're retiring? He said, yes. Dongping is always sure of what to say. And I said, so what are you going to do? And this was a surprise. He said, I don't know. He said, I'll go teach Taiwan, Hong Kong, and come back, maybe settle in somewhere around this area or whatever. And I said, but what exactly are you going to do? He said, I'm going to write a book. And I was so excited. I'm thinking, it's going to be a book on physical oceanography, right? And I said, what is it going to be about? He said, it's going to be about religion, Christianity. What? And, so after the talk, you might want to ask him. Okay.
Yeah, first I welcome new students. Actually, Josie mentioned, I got into this topic actually when I was in Taiwan. I just by accident walked into a seminar in computer science. And the reason I walked into it because the title is interesting. This is talking about face recognition. This, as you know, these days we are all being watched. And so a big thing is actually how do you very quickly process by computer, say, a lot of pictures and identify a person. And they are so advanced that actually people are looking at the problem like, if I take a video like I walk here, and if you take a lot of videos, how do you identify a person by processing the videos? And so it becomes mathematical language, and the image itself actually moving. So after the talk, I talked to the speaker and introduced myself, said I'm kind of decent oceanographer. And so I told him how we do this. And then he was laughing at me, saying, he couldn't believe how primitive we are doing. So I eventually decided to learn something. And when I learned the technique, not that advanced one, I haven't figured that out. And then I had to find something to do with the technique. And that's how I got into this problem. So I think it's important the student try to go to seminars that has totally sounds irrelevant to what you're doing. Because you never know what you're going to learn. Okay? So today's talk, I gave this title to Josie about a month ago. And to my surprise, 2 weeks later, the IPCC new draft report was leaked. I think these days everything is leaked. And so I had to feel important to show you the conclusion of IPCC report in terms of this particular topic. It says that it is very high confidence, which in IPC that means there's a 95% confidence in that. Okay? There are a couple of climate models provide a realistic response to external forcing. External, of course, in this means anthropogenic forcing. This is evident from simulations of the surface temperature on continental and large scales, and the global scale surface temperature increase over the historical period, especially the last 50 years. So basically, IPCC conclude from their massive study that they have very high confidence that the climate models are able to do this. This is very important because the only way you can know the futures or predict the future, you need a model. Okay? There's no other way you can do that. And therefore, it's very, very important that they make such announcement. Okay? So what I'm going to do today is basically focus on this part, global scale surface temperature. Okay? The SST is important, as you know. When you see the SST anomaly, which is basically what we're talking about today, SST is not just at the surface. Okay? So it actually penetrates down to several hundred meters. So basically, the estimate is the heat that Earth receives right now, the so-called excess heat, 90% are actually in the ocean, because ocean take a lot. So it's this huge heat capacity. Okay? So that's like very important because that means there's a long memory. So when you're looking into regional climate change, it's almost all controlled by SST. Okay? So it's very important. Now for people like myself, which actually is working in coastal oceanography, the SST is very important because whatever the SST outside essentially highly correlated with whatever SST inside at the coast. Okay? So it has a tremendous impact on coastal ecosystem because that's basically how things change if the ecosystem depends on temperature. Okay? In the first two slides, I will try to explain to you what IPCC report comes out. Okay? And starting from the third slide, I will try to tell you that this may not be true. Okay? So that's basically how this is going to range. So the first slide is observed global average SST. So basically, we know you have summer, winter, so we're not interested. You take out the signal, and from now on, everything I'm going to talk to you is basically non-signal. We call this anomaly. That means the difference, take out the mean, and just look at change. Okay? So this is basically a record starting from 1880 up to today, actually last year. Okay? And I will come back to what observed means. So let's say this is observed. Okay? And so the fluctuation is actually observations. So it's, in this case, every point is actually signal mean. Okay? But you can just think. So what you see here, all this fluctuation at time scale of a few years. And this is very long, this 100 years. Okay? And this is well known. This is El Nino. Okay? And so we all know El Nino's internal variabilities are marked here. You see this is the 1997, 1998. That's the biggest one. You can see it shoots the whole globe by a lot increase. Okay? Then the dashed line is just a smooth line drawing through these curves. Okay? And so the conventional wisdom will say that, look this record, we have this very rapid change, and we know it's El Nino and it's internal variability. Okay? And so then this gradual change got to be due to external forcing. Okay? So that's the basic idea. So now you can see, let's just put emphasis on this part, which is basically IPCC part. Okay? You can see for the last 30 years or so, the global average temperature has increased by roughly, say, 4 degrees. That's a huge increase. Okay? And so that's basically why we're so worried about global warming issue. Okay? So now I get back to what observed means. Observe, okay, in this period of time is by satellite. This is global average. So you can think about, you take a whole globe, and you take, in this case, the quote-unquote data is actually 1 by 1 degree. Okay? So every 1 by 1 degree, you will have, if you want to know some kind of non-signal, then presumably you have at least have 1 point every month, right? Which is not very good, but that's kind of at least you need to have. Okay? And so that's not a problem in the satellite area. because you can map whole growth. But imagine before the cell line period, okay, it's highly unlikely, as you would imagine, that you will have measurements over the whole growth everywhere. Okay? So essentially, all these data are reconstructed from very sparse shift measurements. Okay? So how much can you trust that is really an issue. Okay? This is really come from a magic computer program that take the shift data and then come up with this called green analysis of gridded data. Okay? So how good of this, we have really no idea. So the good thing is we'll basically focus on this part when there's a very rapid change that we know for sure. And that's basically the period I'm going to work on. Okay? So, but generally speaking, that's basically the curve. Okay? So the reason why I put a question mark here is the following. Okay? So this is a smooth curve I just draw through. You can draw another smooth curve if you wish. Okay? And look at difference between two, and you say that represents some kind of decadal variability. Okay. So the bottom line is that we all believe the internal variety is more than just this interannual stuff. Okay? So if I would draw this curve, say like this, okay, then I just take the difference between this and that dashed line, and I say this is some kind of decadal oscillations. Okay? So that's the key part. The other way to say is that there's no way you will know whether this is actually this. Okay? There's no possibility from observation alone to tell us. Okay? So that's why model is very, very important. So now let's see how model does. Okay? So I pick one example, one model, but basically kind of similar. So the model I pick in this case is the NCAR CCSM4 that's used in this IPCC fifth assessment. Okay, now many models, but NCAR is sort of academic type, so I pick one. So how model does things? Okay, that's basic example I will show you. So that's a nice thing with observations. The reason why we have this problem is we only have one Earth, okay, and we have simulation, and so whatever you measure is what already affected. Okay. So ideally, what you'd like to have as a parallel universe, another Earth, which is exactly like ours, okay, except there's no simulation. Then you can compare the two. And you can't really do that. But there's no problem with model, okay? Because you have a model, and assuming this model represents this Earth, okay, then you can just shut down the simulation in the model, okay, and look what it looks like, and then compare with one that with simulation. And that's basically what IPCC strategy is, and that's basically what I'm trying to show here. Okay? So the nature run is basically a model simulation, then you shut down the simulation. Okay? So it has everything except human influence. Okay? So that's the basic green curves you see here. Okay? Again, you see this interannual, that's El Nino type stuff. But one thing you'll notice immediately is that there's not much warming. Yes? Yeah, that's anomaly.
Okay, so it's not
Everything anomaly, yeah. So it's basically from minus 0.6 to plus 0.6. Okay. So if you look at the green line, you don't really see much change. Okay? And the red line is what we call the force run. That means you put simulation into it. Okay? So it has external forcing. And then you can see, again, forget about that part, as I said before, I'm not going to worry about for a moment. But just look at this part, you can see very clearly there's a warming. Okay? And so if you look at this against that, there's no doubt. Okay? The warming, you would say the warming of this one is due to the human activities. Okay? So that's a basic argument. Okay? So in this particular model, you can see it's probably overshot a little bit. But generally speaking, it follows this curve quite well. See? You can just see it. Okay? If I would draw a smooth line through here, the agreement is actually outstanding. Because it agrees so well, for anybody who has that model, then you must be skeptical. Okay? But remember I told you that this blue curve is the one I come from before. There's no guarantee this blue curve actually represents the external forcing parts. Because you can have internal variability. Okay? And so the fact it follows so well, they make you to kind of think that the model maybe is trying to adjust it or doing something with a target, try to fit this curve. And as it turns out, there are many models from all over the world, from many, many nations. In this particular case, this one kind of overshot a little bit, but you can guarantee there must be another model if everybody's looking at the same curves, must be underpredicted a little bit. So if you take all 20 models and average them all together, you will find you actually get an excellent agreement with this curve. Okay? So that's basically that. When you try to shoot a target, you will miss somebody, will overshot a bit, will be on the left and right. If you take average them all together like a Gaussian, and then eventually you will agree very well. And that's basically the basis of IPCC's report, says that they have a very high confidence that this must be due to unstable. There is no doubt. You can see the change here, even you can see all this El Niño type stuff, they are so far different from this curve. So there are two problems here. One I already said many times, is this target itself will be wrong, right? Because there may be some kind of decadal type of variability that is in this target. And so the part actually due to the false part may not actually be this. So everybody is shooting the same target, but target itself may be wrong. But this is hard, okay? So we'll come to that at the very end of my talk, okay? There's another possibility, which I said, okay? Since everybody's shooting the same target, they are adjusting their model to shoot this target. So just by looking at this, it's not necessarily clear that model actually does a good job, apart from getting this target, okay? So what I'm doing here is basically trying to look into the global SST pattern that come out from the model. Okay, because this one we can compare with observations. Okay, and so that's basically the rest of my talk. Okay, just give you an example. Okay, so this is real data. Remember I mentioned 1997-98 is the biggest El Niño. Okay, so this you look at down this. Okay, and this again all anomalies. So the typical convention for El Niño is year zero means the year that El Niño started. Okay, and so what you will see is the El Niño probably you start seeing them in early spring, and they become much stronger by the end of the year. They become very, very strong. Okay, and so that's Christmas time, and that's how the word El Niño origin comes from. Okay, so that's basically you see this, and all the rest basically what I did just move one pedal up. So you move this up, move this up, and move this up. So if you look at this column, so this basically will start from here and going down to September, the fall of the next year. Okay, and so you see what happened in El Niño is it gets the strongest around this time, and then gradually decay and transition from a warm event to a cold event. Okay, so that's a typical El Niño. Okay. So what I did with the analysis is basically I take the data and pile them just like you see here. Okay. So you can consider each as one sample, which is basically one season. So if I look at 30-year data, I have 120 of this 120 of them. And each one has these 5 patterns. Okay. So then you basically apply a standard technique known as principal component analysis, which is widely used in every field. Actually, was originally developed in psychology, and in atmospheric sciences known as EOF, but it's basically the same thing. So basically, what the technique try to do is try to find what are the most common patterns that you look 120 of them all together. Okay, and so you identify this common pattern. Then for each sample, you give them a score. So if the score is high, that means it looks just like that pattern. And if score is 0, means there's no relationship at all. Okay? So once you find the first pattern, then you go to find the second pattern, which is common, and then you give them a score and so on and so forth. Okay? So in principle, it's quite simple. In practice, in this particular problem, it's actually very difficult. The reason is because it's a very large data set. Okay? And as I mentioned, that's how I learned from this computer science field. So if you just look at these pictures, you can just guess what the dominant pattern would be. Okay? These are typical El Niño patterns. Okay? And since El Niño is the dominant global SST fluctuation, so you will see the dominant pattern must look just like that. Okay? And then from the second pattern, it will be sort of like that because they're so different from this. And it represents a transition from either warm to cold or from cold to warm. Okay? In all these analyses, it's linear, so it doesn't depend on the sign. Okay? So if it's a cold event, just everybody is cold. Just change them to blue. Okay? So that's basically how this works. And it turns out that's actually true. So this is from model. Okay? So from the nature of them, without human activities, you look at the model, output I already showed you before, and see what the dominant global SST pattern in there. And it turns out the dominant two modes which dominate the whole thing. Okay? So again, these are seasons, each one is one seasons. Okay? And the first mode, just like El Nino. Okay? And that we call them typical, so we call them canonical El Nino. They tend to be in the central eastern Pacific, on the tropical regions. Okay? And then the second mode, in fact, is this transition. Okay? And so in this case, it's transitioning from cold to warm, and you can just flip sign and we'll go from warm to cold. It's no difference. Okay? And so then that's basically what we find, the typical case. And so that says model does very well. Okay? Because that's exactly what you expect. Okay? So once we know what the nature run is, then we can look at the force run. So to see what human activity does to these guys. So you take the same data set, now this force run, and go through exactly the same analysis, and you find there are three modes that dominate, okay? But these two actually is just flip side, okay? So just look at mode one first, just like what you saw before, okay? If you look really detailed carefully, you can see that's warming here, that's yellowish here, okay? So the mode one is very much like the character you saw before. So what external forcing does to the warm one is make it a little bit warmer here. Okay? So somehow external forcing project onto this nature mode, okay? And make them a little bit warmer here. And the second mode is also very much like what we saw before. The only real difference you can see that's this two parts. One's on the central North Pacific and one's on the central South Pacific. You have these two warm bands here, which in the nature mode also there but very weak. Now becoming stronger, you can see here, you can actually see the red. Okay? So that's second mode. So again, it says somehow internal forcing project, they are not major, but they do affect a little bit. But now the third mode is quite different. Okay? Let me make it down. Okay. So if you just look at equator, it looks like transition, just the opposite, right? This is from cold to warm, this is from warm to cold. So that's basically just a transition, okay? But now you see all this red everywhere, okay? So that means the eternal mode, in this case, completely overwhelm what the El Nino should look like, okay? Now you make everybody warm, essentially everywhere, okay? So just by looking at this picture, you can guess, okay? And this is probably one that will be most responsible for what we see in the global mean rise, okay? And it turns out this is indeed true. If you take these three modes, which explain about 50% variance, and this actually explains 99% of the global mean.
Are those normalized?
Say it again?
Are those normalized?
Yeah, so each one is normalized by itself.
What amount of variance is that one mode explains?
This is about 25%, each one is about 10%.
So that's pretty considerable.
Yeah. Okay, so you see this one, then you can guess that this is probably is what happened. The global warming, according to the model, is probably mostly controlled by this one. And we can also see that, to confirm that, we can look this way. Let's spread. So the top one is known as a Nino 3.4. That's a convention index, which basically is just the average temperature around the central eastern Pacific in the tropical region. Okay? So it's a convention index everybody use to denote whether you have a warm or cold El Nino event. So whenever you see these guys going up, that's warm. Whenever it goes down, that's cold. Okay? Don't worry about those events here because it's a nature variability, so they're not going to line up with actual observed. It doesn't matter as far as the model is concerned. But model obviously shows up and down. Okay. The PC1, PC2, and PC3, this is what by score. Okay. So that's basically the projection of every season or every year onto these three modes I just showed. Okay. And one thing is immediately PC1 just look like the 3.4, which is not surprising because, like I said, the first mode is canonical, so it's like a typical El Nino. Okay? And therefore, there's no surprise, it looks just like El Nino. Okay? The second one can shift a little bit, remember, it's actually the transition. Okay? So they actually did ahead of that one a little bit, but they saw it still like it. Okay? And the third one still has some El Nino, but once it becomes very obvious, you can see this one, that's a warming trend. Okay? So it's all kind of minus here and all become plus there. Okay? Everything relative, average of all these is zero. Okay? So you can see a very clear warming trend. Okay? And if you look really carefully, which is really hard, but you can do that if you actually plot the other way without, if you just plot line without this bar chart type. And this one actually also have a slight warming trend. Even though the two look very similar, just look this guy goes all the way down to here, but now it only goes a little bit. Okay? So you can actually show this guy also has a warming trend. Okay? So in this case, basically, mode 1 and the mode 3 all has warming trend. Now you try to quantify them, that's the number right here. Okay? So it turns out the mode 1 will contribute 37% of the global mean, what you see there. In terms of warming trend itself, it's about 1/3. Okay? And this one will contribute 55% of the global mean. And in terms of trend, that takes about 2/3. And you add them all together, that's 99%. That's basically what I said. So basically, you take these three modes together, you explain everything you see in terms of global mean. So what this says is, according to the model, okay, this is basically what happened. When you put human activity into that, you project into the mode 3, I'm not going to flip back, can't cover everything. Okay? But you also project into this typical El Nino mode and make them actually warmer a little bit, and warmer, which is actually consistent with the theoretical argument that when you have a warmer climate, you tend to have something like this one. Okay? So another way you can do it, is the easy way to do it, is just see what it actually looks like if you look at the whole Earth, and that's the next picture. So basically, I just compute the linear trend at every grid point for this period. Okay? So that's basically contributed by that three modes. Okay? And this is what you see. Okay? Now look at the scale. Okay? So the counter line here, everyone is 0.1. Okay? That means 0.1 degree per decade. Okay? And so the color changed from mine, but basically this is zero. Okay, so everything you see here, all this part, essentially almost 0.1. Okay, the global average in this case is 0.11. Okay, and you have some hot spot here, some hot spot there, some hot spot there. But by and large, okay, if you do these pictures, then that's basically the state here. Okay, and space says that if you take a look at a model, okay, if you just want to look at the global mean, okay, and essentially it's warming is everywhere, and essentially 0.1 in this case. Okay, so that is, I think everybody read my abstract. That's why I use the word common means. Okay, that's what everybody believes. Okay, so people take that as if they are truths. Okay, and because all the models essentially all show the same results. That you have essentially warming, the minor details, but essentially warming everywhere. Okay. So that's model. Okay. So the nice thing, as I said before, because now we are not looking at the future, but looking at a period which we actually have observations. Okay. So now we want to know what the observation says. So I take the satellite period, which is about 30 years, and then 82 to 2012, okay? And I do exactly the same analysis, okay? And so these observations, again, that's mode 1, and just like a model, okay? You can see that's typical El Nino and it's warm up a little bit along. So El Nino is not only equator, but actually spread all the way to both the west side of both the North and South America. Okay? So that again, just like what the model says. Okay? And if you look at translation, that also very much like the model says. Okay? In this case, you have from the warm go to the cold, and in this case from cold to warm. Okay? Now there's a big difference, which again the color change a bit, make it harder. Look at this one. Okay? We actually go back so you can see it better. Okay? In the model, if you look at the second mode, there's not much going on in the North Atlantic. Okay? So the action is in these two parts, but not North Atlantic, and this, of course, everybody's warm. So now in this one, you look at both modes, you can see there's a lot of things going on in the North Atlantic. Just look, this all become red. Okay? And now in the Pacific side, and this again, just like observation, just like a model, you have one band here and one band there, both in the kind of mid latitudes, one in the central North Pacific, and another one in the central South Pacific. Okay? So if you look at these pictures against what you saw before, is that according to observations, what happens if we believe the nature run is correct. Okay? So we have to start from somewhere because we don't have a parallel universe. I already told you that. Okay? So if you believe the nature run is correct, then what the external forcing does to the real world is actually produce a lot of warmings along the North Atlantic, okay, as well as somewhere over here. Okay? It doesn't really affect much of this the typical El Nino features. Okay? So if you look, the first two looks about the same, the last one obviously.
What are the eigenvalues here?
That again is about 20-some%. Each one is about 10%. So add three together is about 50%. The ratio is actually very close to about 2. Okay, so this is about probably 22. This is about 30. That's about 11. Okay. So again, then we can look at the time series, and that's what you see here. So this is the Nino Swift down. This is real world. Okay. So this is actually the 1997-98 El Nino, okay? The biggest one. Okay? So that's the El Nino. Okay? That's the first three mode plot here. Okay? So let's first look at mode 1. Okay? So the mode 1, you can see it looks like this guy because it's canonical. Okay? But I don't have to tell you, you can tell it's become much colder as you go. Okay, so that's why I say PC1 is cooled down a lot. You just look at this. Okay. So let's don't worry about it for a moment. Let's look at PC2 and PC3. Once it's very obvious, both are warming up. Okay, and then you can also see they all have this error signal. One is ahead, one is behind. Because one is basically, if you look at that. So this will describe. You go from cold to warm, and this guy from warm to cold. Okay? So one is lag behind this, and one is ahead of it. Okay? And that's basically what you see here. Okay? So also I put 3 numbers here. Okay? So that's basically, so if I take these 3 modes and try to reconstruct global SST, and you find them. The mode 2 explains 40%, and the mode 3 explains 49%, and the mode 1 has almost no effect at all on global mean, even though it is the largest signal. Okay? So what happened basically is that the warm part and cold part just cancel each other. Okay? So when you add more together, basically there's no effect. Okay? And you add all these 3 numbers together, that's about 92%. Okay? So if you want to plot curves, they basically look very similar. Okay? So what this says is, according to observations, okay, the global warming external forcing is projected onto these 2 modes, the transition mode, okay, and this is the canonical mode. Okay? Now for this one, I just say a few words, we'll say a little more later. You can see for people who are interested in El Nino itself, and this is really dramatic, okay? Because look at all these things. So if you look at this part, you say this El Nino is just controlled by this part. Okay? That's what we call typical canonical. Okay? But now look at this warming event here, or warming event here, and there's almost no contribution from the canonical mode. Okay? What it says is that any El Nino you see after year 2000, it don't look like a typical El Nino anymore. Okay? Because none of them, they all come from here. Okay? All these products are the same scale. Okay? And so the contribution is just added numerically. So score 1 plus score 2 plus score 3, just add. Okay? And so it says all the El Ninos after 2000, there's no such thing as typical El Nino anymore. Okay? So that generates a lot of excitement for people who are interested in El Nino, okay? Because they find what's known as the Eastern Pacific El Nino, which is a typical El Nino, is no longer there. And people, of course, write all kinds of theories trying to say why. Okay? But that's not what I do here. Okay? But it's very dramatic. Okay. So now you can also ask the same questions. What now the global acidity look like? So let me get back one more time so you see it again. Okay. So basically it says that with these two modes, you see a lot of warming along the North Atlantic, and you also see warming along here. Okay? For the first mode, it's actually cooling, right? When you saw the curves. But I say for the global, they have no effect because whatever the warm parts just add up, cancelled by the cold part, the blue parts on two sides. Okay? But it's cooling, that's the question. Okay? So now you add them all three together and try to see what you get. That's what you get. Okay? So the scale here changed, but contour interval is the same. Okay? So each contour interval is 0.1 degree a decade. Okay? So you don't have to look very carefully, you can see they look very, very different from what the model says. And there's no such thing as uniform warming. Okay? But now let's look more carefully what it does. Okay? So let's look at this one first. Okay? It's all yellowish, it's all positive. Okay? The digital line is you can't see it from far or even here, but this digital line, so this is 0.1, 0.2, this by 0.1, 0.2, 0.3, 0.4, and it goes up there. Okay? So if you want to go to, as I was talking to Mary, you can see they're all red here. Okay? So temperature rise there is almost like 1 degree per decade. Okay? So this whole part of the world has completely changed. Okay?
So is this the actual observed warming trend, or is this the warming trend from the first 3 EOFs?
Say again?
So is this the warming trend from the data, or is it the warming trend from the first 3 EOFs of the data?
This is from data.
Okay.
Just take
So
the
whole
temperature
thing.
data.
Okay.
So, but we can see, so this of course is consistent with what you just see, the 3 modes, okay? Because 3 modes expect 93% after all, okay? And so all this yellowish one is warming, they're all very big numbers, okay? In the US part, that's actually a cool part, right at Georgia and Florida. If you actually look, there's a blue line here, okay? So people are thinking about maybe sculpture move in and out, I have no idea. But basically, the Northern Europe, and Canada is very, very hot.
So, Don Pig, what's causing that warming in the Arctic Ocean there?
I'm not going to explain what caused it. I'm just trying to compare. Okay? There's a bigger models there. Okay? So trying to explain what caused it is actually not very useful question, I think. Okay? So, so you see very high temperature rise here, relatively high here, and I think this is probably zero here, 0.1, 0.2. So you see these big parts here. Okay? And you see 2 big parts there, as I said before, the 2 warming here. But remember, I also told you that even though the mode 1 has no contribution to the global mean, it's the biggest signal, okay? And it's cooling. So the diesel line is actually this line. So all this blue is actually cooling. Okay? So entire West Coast America is actually being cooled down in the last 30 years. Okay? So if you live in California, that's probably about 0.3 or 0.4 degree per decade. California is cooled down by about 1 degree. last 30 years. Okay, so all this is just because the big signal in the mode 1 is cooled down. Okay, and because mode 1 is cooled down, so it will make this even warmer, and that's why you see yellow here. But like Indian Ocean, all that, there's nothing happening. Okay, if you take all the average together, the number is actually 0.07. Okay, which is not even in one of that. So you can see the global warming is highly non-uniform, if I use that word. Okay, and you see big warming here and big warming that side. Okay, so for this one, the mode 1, as I told you before, okay, because the pattern doesn't change. So if I would just use based on assuming that nature run is what real should be if there's no civilization. Okay, so I will argue this is probably some of the natural process. Okay, first it's cooling down, so it's not very good because you add heat into the system, and it cool down like crazy too. Okay, much faster than any of this. Okay, so this probably is a natural process. Okay, and therefore, when you look at this signal, you can't say, you can if you want, but it's probably not good to say that the global warming caused this one. Okay, they are probably not part of the global warming signal, which is part of the internal signal. And of course, that makes life very difficult, and that's really what I try to point out. Okay, so that's what actually happens. And basis, what happened in terms of external forcing is actually being projected onto this transition mode in El Nino and affect entire group. Okay, since we do have some ITP, and you know, if you can change temperature by that much, the sea level pressure must change. Okay, because to make things anyway, once you are outside the equatorial regions, okay, if you want to cool something, you probably have to decrease wind because they can be flat in the big things. Okay, and so this is trend for sea level pressure. Okay, so what you find is over this part of the world. Okay, I think for most people know there should be high pressure here, Bermuda High, and that's low pressure here, which is the Iceland low. Okay, so what happened this part of the world is this system is being weakened. Okay, because the high part you actually add the minus here, and low part you add the plus here, and that of course is correspond to this tremendous warming in this part of the world. Okay.
So is this based on NSEP?
And 70 yes. Okay, and over here, you can for people who have taken a core course, you know the El Nino is actually also called ENSO because the El Nino signal with the warming along the equator is highly correlated with the sea level pressure change. So the wind and the season temperature, of course, are also back and forth, and that's usually measured by sea level pressure difference from here and there. So you can see this actually increase. Okay, so that means what we usually call Walker circulation, which is Walker first figured out. The Walker circulation actually becomes stronger during this period of time. Okay, so if you are interested in detail about that, I believe in the next Wednesday's ITPA seminar, the speaker will talk a lot about what she studied a lot of these regions. Okay, but there's no doubt just look that. And the whole Antarctic part, it has a very low pressure. And so the wind over there getting stronger now. Okay? And that's also, I think, well known. Okay? The Northern Pacific, I don't ask me what that is, but that's what you see. Okay? And so that's the sea level pressure that corresponding to the same chart. Okay? So the sea level pressure on this and on that is fully consistent with what we will expect. Okay? So the other way to say is that the climate model somehow is not able to do that. Okay, I don't want to show you how bad it looks like, but the fact that the climate model gives you warming everywhere, that means it's not able to get some pattern.
So Don Ping, those changes in sea level pressure, what does that translate into in changes in the geostrophic winds, large-scale wind patterns? Are we talking about?
I'm not going to talk about that. So I will get the last one. Okay. So everything I've said so far is the fact that if you assume Okay? If you assume that what we saw in the global season temperature rise in the last 30 years is due to external force. If you assume that, okay, then what I just showed you is the fact that the climate model is not able to show what actually happened. Okay? Climate model basically says warming everywhere, but in reality, what you saw is you have very strong warming in North Atlantic and you have very strong warming in the Central, North, and South Pacific. Okay? The last line shown here is, remember I started the whole thing by saying that this target that every climate model tries to reach itself may not be right. We may be looking at the wrong target. Okay? That's more philosophical questions, but I will try to convince you that may not be so philosophical either. Okay? So it's well known. What I mean by well known is nobody will charge you that if you write a paper on it. Okay? It's well known that North Atlantic temperature has a very large internal variability, and it's known as Atlantic multi-decadal oscillation. Okay? So everybody agrees with that, and if you look at IPC report, they also agree with that. Okay? So, and there's many theories try to explain why, and so, but everybody agrees it's an internal variability. Okay? So now I put a question mark there, that means I may not agree with it. Okay? So let's look what that is. So how do you determine, how do you describe AMO? Okay? So that's always an index, okay, known as the AMO index. So the idea is very simple. Okay? You observe the North Atlantic temperature average over the whole North Atlantic, okay? And you may minus what you believe is the force part. So that's very simple, right? There's force plus internal. And I know sum together. So if I know what the force part is, I just take them out and what I get internal. Okay? The hard part, of course, you don't really know what the force part is. Okay? So people try many different techniques. Okay? So one of people believe the best approach is basically use climate model. Okay? So use the climate model to figure out what's the force part of the North Atlantic temperature is. Okay? There's only one problem, as you already saw here. The climate model does not really predict what should be the force part of the North Atlantic temperature. Okay? So that's the model approach. Now there's another approach, which we say we don't really like a model. So we think, because remember I told you that everybody believes the global warming is essentially uniform everywhere. So I just take the global mean temperature, which I can measure, and subtract it out. And it turns out, whether you use a model approach or use the other approach, basically gives you the same result. Because model also predict the global temperature is uniform everywhere. So whatever in North Atlantic is essentially the same everywhere. Okay? And that's what you see here on the left. Okay? So the blue line is measured the North Atlantic temperature for the 30-year period. Okay? The red line is the global observed mean temperature. Okay? So here again, if you just look at slope, okay, you can see the North Atlantic temperature rise about 0.8 degree per year, but the global temperature rise is about 0.2. Okay, so it's basically rise about 3 times faster, and that's basically the picture we saw before. Okay, so if you take difference between these two, you're very happy because this is only 1, that's a 3, so they are so just like the blue lines. Okay, and that basically gives what known as the AMO for the last 3 years. So the AMO is rising. Okay? But now, before I show you that, now if we believe what I just told you, take the same hypothesis, because I have 3 modes, so I can reconstruct the global temperature, which I already showed you agrees well with observed. I can also reconstruct the North Atlantic temperature based on that 3 modes, which of course I will call an external force. Then they have to be, because that's the hypothesis that stops. Okay? And that's what you see. So the blue line is the same one, and the red line is the one that reconstruct from the 3 modes. Okay? It's not surprising because I told you that most of the heating occurs in North Atlantic. Okay? And the curves are essentially identical, almost. Okay? So if you want to take a difference between that, then you say there's no such thing as AMO. in the last 30 years when we have the best data. Okay, so that's basically where we end up. Okay. So I think we have two scenarios that I can think about. One is the hypothesis is correct. Okay, that means what we saw in the last 30 years, the mean rise is essentially all due to external forcing. Okay, so the model is not very good in this case. Okay, then the climate prediction was severely underestimated the North Atlantic warming, because North Atlantic actually warms 3 times faster than global mean. Okay, and so if you take the climate prediction from IPCC and say this is what North Atlantic should look like, you'll be tremendously underestimated. And that's, of course, a very serious problem, especially for people living in Canada or Northern Europe. Okay? So that's another possibility, which says that external forcing is not so real. I don't want to say it's false. Okay? So that means the curve you see there is not entirely, or even 50% due to external forcing. Okay? Maybe only 20% if you really like AMO. Okay? And we have no idea, I always said many times. You cannot determine that solely by observation. Okay? And so in this case, if it turns out the curve that you see now 30 years only say 20% are due to external forcing, then obviously the climate model prediction is grossly overstated. Okay? And so whether you like one or two, I think both will have tremendous positive implications on climate change. And so if you read IPCC draft report, okay, and when they describe how wonderful, what high confidence they have on their success, okay, they do list what they consider the number one issue in future uncertainty, okay, which is basically I call here with our red one, that was add, okay. It says robustness of detection is subject to climate models correctly simulating internal variability. So what it really meant, if you read the whole paragraph, is they think they've done such a wonderful job in terms of simulating El Nino, all this stuff. So the only thing we are not 100% sure is the fact that as this decadal variability, that people believe they are there. But the current model cannot do that. So they figure out this is probably secondary, but it kind of be nice to improve that. Okay? But if you see what I just show you is that it turns out the external forcing is actually project, if we believe in scenario 1, okay? It's actually project up to El Nino, okay? And the climate model has no idea how to do it, okay? And so I add this red part here, okay? So I think the real issue is that because climate definitely has El Nino actually looks very nice, okay? But it couldn't really properly project external forcing onto El Nino, the warming parts. And El Nino has tremendous effect globally. It's the single largest SZT variability globally. And therefore it messed up everything else. Okay? And so I think, as I try to conclude here, that's probably what one really should try to improve. And instead of just worrying all this about whether how good and nice, because we are way off, far from what real world actually shows. Okay, thank you. Yes?
Yeah, you say climate models wrong there, that, but it's only one model that you showed. Have you looked at other models?
I thought that's a student's business. Okay, I mentioned about this one, the north sun temperature. So when people try to determine AMO, Ting, I don't really know her, she actually compared 5 different models from same IP3. Okay, there's another fellow actually looked about 20 models. They say all models are consistent in a sense. They all basically say the north sun temperature is about same as global temperature.
But do they also, all of them don't have this shoe horse pattern that you see in observations? For this trend, for warming trend,
Mhm.
this horseshoe pattern?
Yeah.
Do they all don't have that?
The warming trend in North Atlantic?
Yeah, does this cooling?
Yeah, the cooling part they don't, because it,
All of them
no,
don't have
nobody
it?
can have it. But that's, I think it does. You mean this one,
Yes.
this guy?
Yeah. This is
This
just
one?
one. Yeah. This is.
Oh, I don't want model. I don't. For the moment, I would say that internal, because that would be another degree of complexity added into the problem. Yeah, what you're really saying is that this, whether this is due to external force or not. No, nobody. I don't see anybody.
You do this far-fetched conclusion based on one specific model, which is not really the best one.
Yeah. But I think that's what I meant by student. Actually, I also looked at the GFDLC. So I look at two American models. They may be very bad. I agree with you. But how good CCSM? I think you had to ask Ming Hua. I believe he chaired the CCM advisory panel, right? So no, I can't say anything. I already told you that I'm totally ignorant about climate model. I'm just showing you the results. But I think it should be a very good project for students to look at every model, as you say, because people didn't look at it. They are looking to statistics, which, as far as I'm concerned, everybody is looking at the wrong point. Yes.
I have a statistical question, which might be naive. This principal components analysis is giving three components that are supposedly statistically unlinked to each other. That's the basis of the analysis, as I understand it. But there are loadings that determine these components, and as far as I can see, it can only be geography or time that's loading on the three. So my question is how much overlap is there in loadings, even though they're behaving? Are 2 and 3 strongly overlapping in the loadings?
Yeah, they're highly correlated, each one.
Right.
Because it's phase length. So one is ahead, one is behind.
So basically, you're sorting geography
Okay.
more than anything else.
I think that you raised two questions. Okay. One question is the point is that the PCA look each mode as separate. Maybe I should do this. Better just show that. Okay. For the purpose of this talk, because I'm not trying to explain what that is. Okay. I think Mark already asked many times. Okay. So for the purpose of this talk, okay, all this does is just try to reduce the data size, which is basically the same thing computer science people doing with face recognition. Okay. It just reduce the amount of data into this. These two, are they related? They definitely are, because because this is going down, and it's from warm to cold, and this from cold to warm, so they're definitely related to and they are off by 3 seasons, as you can see. So this is basically the same as, not the same, but similar to that.
But I can ask the same question differently. Actually, so this is very interesting, but I think we have to be careful in interpreting PC2 and PC3 because their eigenvalues are very close to each other.
No, they are not.
So no, you said it's 11% and 13%, right?
Yeah,
So
no,
we know this that if two eigenvalues are close to each other, then their patterns are degenerate. You cannot determine them technically.
This
So we
is
can
13,
just-
this is 10.
Yeah, so that should be tested and.
But I think, I know what I said, but I think the important part is if I would just do the reconstruction, so I don't really care what they mean. I say that if I would take this one, take a picture, I can reconstruct that one, and then, more importantly,
So if you.
this has nothing to do with any of
Yeah,
the
yeah, so that is a separate question.
You see what I'm saying? So this has nothing to do with PCA or anything.
But it does matter because PC1 explains such a tiny percentage
Yeah.
of the overall variance, and the other two explain very high percentages.
No.
Oh, no. You're
No, but they are very
misunderstanding.
close to each
It's
other, so
by your average over
their
the
individual
whole thing.
patterns are not determined.
Yeah, formally that they don't, just because they have high values doesn't
No.
mean they
No,
have
no.
to be degenerate, but.
We-
Let me do
it's-
that.
it's
No, it's
required.
probably my fault. I didn't explain clearly. What I meant is that the PC1 is the largest one. Okay, they explain about 24% of the variance. Okay, what I meant is that if you take the SST average over the whole domain, over the whole globe, So the PC1 has a little contribution to the global mean. PC1 is the biggest signal in the Pacific. Okay, so that's probably my fault. Okay, so if you average the PC1 over the whole globe, then you can see it's all blue here and red there. Everybody else is blue, just this big red. So if you average them all together,
Then it's 24%.
yeah, they
And
only.
the other ones are lower than.
Yeah.
Now you just answered this, my second question is, how did you get a PC1 so low? It's the fact that it's high.
I didn't make that clear. But that's why you see PC1 so heavy here. Okay. Very good. Any questions? Yes?
Yeah, so mode 3 is like a global warming,
Yeah.
and that's in both the observation and in the model.
Mode 3.
Yeah, mode 3, mode 3.
Okay. In the model, in observation, the 2 and 3, but let's just call them together.
Yeah.
It's just called translation. Okay. So yes, and that's also true in the model exactly. So basically, what it says that, but I have to take go back a bit. Okay. So the model actually has six runs. Okay. There are 6 different model runs. Yeah, well, I actually have a picture. Since you have that questions. Oh, here we go. Okay. So the model actually has 6 runs. So that's again nice thing to the model. Okay. So there are 6 different runs with exactly the same forcing. You just change the initial condition a little bit. Okay. Because the model is highly nonlinear nature, it's kind of complicated. Okay. And what you found is that in the 6 runs, okay, they are always dominated either by PC1 or PC3, or in the case I just showed you both of them. Okay. So that's and that's the basic shows up here. Okay. So the sort of kind of purple one looking, or whatever color, is PC3, and the light blue color is PC1. So just take a quick look, and this is the base case. That's sort of comparable. That's why I choose that, so you can see both of them. Okay. But that's one thing kind of interesting if you really like theory. Okay. So basically, you have exactly the same external forcing, but in the model, the projection actually into different places. Okay. And sometimes in this round, they all go to PC3, which is the translation. Don't worry about 2 and 3. Okay. As far as I'm concerned, they are the same. Okay. But in this case, they all go to PC1. Okay. And so that will almost suggest there's some kind of bifurcation. Okay. It's a classical example of nonlinear system. You can actually project into different modes. Okay. And that by itself, I think, if you're interested in theory, that's a very interesting set of questions. I have no idea why. Okay.
So that basically says the large internal variability
Wow.
within the system.
Yeah.
So at the end, what matters is the ensemble average
Right.
signal. And that average signal seems to be
Yeah.
consistent.
So in this case, all 6 actually give you unity.
Mhm.
Because I think you just have to put a woman somewhere in the model. Yes?
Right, the modes for during the past 30 years, you got 3 modes, and then some mode is one. Was that because the global warming was not so significant during the past 30 years? So that the mode.
That is still without that.
Okay. The modes
Uh-huh.
in the past 30 years, you get the El Nino mode dominant. The global warming mode less significant. Was that because global warming was not so serious during the past 30 years?
Oh,
Let's say during the next 100 years, global warming will be much worse. You know,
I can't answer that question. Yeah. So there was, see, that's the problem with observation. That we have a relatively short period of time, which we know very well. Okay, and so I actually look the record that I don't believe, tell the truth. Okay, I also actually look at the other so-called early warming, which is early beginning of early century. Okay, you also see North Atlantic dominant. Okay, but I have to be very careful about all this because most of measurements are done in the North Atlantic. Okay, and so I think that itself is a very important because we only got 30 years satellite. You wait for another 10 years, you got 40 years. No big deal. Okay, we do have a record that goes back with ship. Okay, I personally do not believe the real analysis. Okay. There are real data there, But you have to do something with that. If you know something about it, maybe you can do something with it. Okay? The real analysis, which everyone use and assume layout data, I don't believe it. Okay? When you have the global coverage less than 20%, and you can tell me what a global mean is by mapping them with 100-year mode, that's just ridiculous. But since it's been done, everybody use it. Okay? But I think that's actually very important question, research issue, is how do you look back, assuming what I said is correct, okay? And assuming this is really what warming goes into the internal mode, okay? The internal fluctuation, then probably you can look back the real data and see whether they're consistent.
Okay, in your view, will those modes change in the future?
They're basically just a translation and the canonical. There's really nothing else. You can't imagine anything beyond that. But I think what this, we have several questions about PCA. What this really says is that if you want to look global, they're essentially all dominated by El Nino. There's nothing else, even though it's only 50%. Okay? And El Nino, how you look at that doesn't really matter. It's just El Nino. Okay? And that's really the bottom line. Because that's the only signal. So basically what it says that the teleconnection is really the part that the model means. We do not know, and it's a difficult problem, everybody knows it. So we know everything starts from tropical Pacific, hopefully, okay? And then somehow this energy propagates away from the tropical Pacific, affect the northern Pacific, southern Pacific, and then somehow jump into the North Atlantic. But we don't know what the physical process really is. I think that's really the bottom line. Okay? And people, in my opinion, okay, now one more question, actually, I'm not going to say that, I'm going to try to allow problem. Okay, any other question? Yes?
Say, when you compare this for the model part, you started from the 1880s to present. But what if you had done the analysis for the model results in the same
the same period?
With the observations? What would you
because in this particular model, it started warming up basically starting from about 1960. And it warms up faster than observed. Okay? So that's why it starts 1960 instead of the same period. But that really doesn't matter, I think, because the nature of it is not the same. There's no way model will match same, because nature is the nature of it. So models El Nino will not line up with observed. There's no possibility, which is perfectly fine. Okay? So we are really looking at the difference between nature and force. And so model itself is fully self-consistent. Yes.
So you're very comfortable with the idea that the El Ninos are not going to line up between the model and observation because the internal, it's an mode of internal variability. But with these decadal modes, they're not going to line up either necessarily. And a multi-decadal mode is as long as your entire analysis period. So it couldn't just be that if you considered a longer time interval and averaged out these longer multi-decadal modes, then you get better
The model itself,
models. And
model won't do that. Observation. I'm not going to say anything bad about it. That's not what my intention here is. Okay? I think this is, if I think we all think global warming is important, and IPCC is the single largest effort. Okay? So you're not going to throw out IPCC and say I'm going to do something. Okay? That's highly unlikely you'll be able to do it. Okay? So one simple way, if any student want to do that, it's very simple, that I think instead of just doing that, you can just, because it's very easy to do. If you have to look each model like what I did here, you go crazy. Still can't do that, and you probably don't want. Okay? But if you would just compare North Atlantic temperature against global mean, that's very easy to do. Okay? And then you will immediately find out what happens. And based on what people have studied, even though they didn't know that, is that the North Atlantic temperature tend to be about the same as global mean. And now in terms decadal variability, okay, I think personally, I think we want to be very careful about that. Take simple example. It's easy to say it, but one really has to be very careful when you say it. So remember I told you that these are these very distinct patterns here, okay? And this is known as PDO. And people looking into the Pacific decadal oscillation will look at this pattern and say, this is typical PDO. Of course, they didn't look at these parts. Okay? They basically just took the North Atlantic and they do their analysis from 20° north and identify something and run a regression. Okay? But if you actually do the SST over the whole globe, that's what I did. That's just a part of this whole El Nino process. Okay? So the whole questions, and the same thing when people do the AMO, they just look at the North Atlantic and they assume North Atlantic has nothing to do with the rest of the globe. So if you actually look at the papers on AMO, some people say, it may have something to do with Gulf of Alaska, and some people say, yeah, they may have something to do with El Nino. You know, they look certain part, okay? But if you look at my picture, they not only may have something to do, they're actually part of the whole thing. Okay? So the problem with a lot of this decadal type of analysis, they basically restrict their domain analysis and tell a story based on that. And so that's one possibility, maybe they're all wrong. That's the example I just showed you.
Okay, thank you very much.